Hello, everybody. My name is Cristóvão. I'm from the University of Lisbon, and I will talk you today about how to use the package LAMMPS for molecular dynamics simulations of active matter. So LAMMPS is an open source, quite complete molecular dynamics package. It was done for materials. It started developing in the 90s. And it's a bit complex, so it has a long learning curve, but we'll try to shorten that a little bit with this class. And I will try to show you a little bit the advantage of this package. We'll have a hands-on session. This one here today will talk about the basic molecular dynamics in LAMMPS, how it's implemented. So you guys already heard about these topics with in other talks with Agnes, Aykut, and Just, but I will just show you how they are implemented in LAMMPS, and then we'll have them. I have divided in 3 videos. So the second video will be about an hands-on introduction, hands-on on LAMMPS. You start the installation and how to run simple scripts. And the third part will be an advanced hands-on, when we'll just implement a new fix or new class in LAMMPS, and I'll show you how to do it for ActiveMatter, and then you'll do some tests. So today I will start by just the outline of this talk, which is just a bit of molecular dynamics. I'll start with the integration of the equations of Newton. So you guys already talked about that, so I'll not go deep into the subject. And then I'll go through the force computation, which is the bottleneck, then the parallel computing, talk a little bit about the Langevin dynamics, which is important in this field. And then we'll try to simulate active Brownian particles later, so I have to use this Langevin dynamics to reach the Brownian regime. And I will finish this talk with the reduced units. And so the velocity varlet integration is similar to the ones that Agnes did in their talk, which she showed you the varlet integration, I think. The velocity varlet is similar, so but you treat explicitly with the velocity. So you don't have the initial velocity problem when you need to add a step to define the velocity. You have it explicitly in integration, and you can do it in 2 steps. Just have a step for the positions from the force computed in the initial position, and then you just have the step for the velocity that use both positions at time t and t plus delta t. These 2 steps has a disadvantage that you have to keep at all time the values of the force for 2 time steps, which is not optimized this way. So what LAMMPS does, and how is it implemented in LAMMPS, is that you have 4 steps. So you start with a step with for the velocity, alpha step for the velocity, when you use the computed force from the previous step. And then you just update the position. So you have a full step for the position from the initial position, then you use the velocities of the half step jump plus the time step, times the time step. And then you compute the force. Now you compute the force at these new positions of t plus delta t. And then you use these new positions for the final half steps of the velocity. So the advantage here is, as you can see, is that you only need to compute the force in the middle of the steps, and you only need to save at all times only one values of forces or acceleration. So Here you have the previous steps, and then you have to compute the force, and then you update the values of the force acceleration, and then you just use it for the next step, which saves some memory usage. Okay, so as you can see here, this is the computing force is an important step, since it's the bottleneck on all molecular dynamics simulations. So why it is a bottleneck? Because if you have pair interactions, for instance, you can have many body interactions. If you have pair interactions, you'll need to check all the pairs of particles. That takes a long time. One possibility to optimize is just to have a cutoff. So you consider that the effect of the potential above this cutoff can be neglected. This is a good approximation for most potentials, except these the long range ones, and then you have to use some different techniques. But if you have a cutoff, you still have to check if the particles are inside the cutoff. So one possibility is just to keep a list of all the neighboring particles that are inside this cutoff. This is called the Verlet list, and this is what LAMMPS use. You have a list of all the particles that are inside the R cut plus some distance of tolerance, that is the skin. So all the particles that are inside the R cut plus the skin, you consider them in the Verlet list. But so this is one possibility. I think you guys already talked about that in previous talks. But this is also not the best optimization, because the one thing that you need to do is that each time that you update the list, you have to check all the particles in the system, and this takes a long time. So the size of the skin is important. So to choose the size of the skin is just kind of a trade-off between, if it's very large size of the skin, you have a lot of particles in your neighbor list. You don't need to update it every time step, so you can keep it a lot of time steps between updates. But the disadvantage is that you have a large list of particles. If you put it too small, the skin, you'd have to update in a lot of time steps. So you just have to check this trade-off, but you still have to update the list following all the particles in the system, just to the update. So one thing that we can use is the cell list. The cell list by itself can be used just to compute the forces, but here LAMMPS uses only to update the neighbor list, the Verlet list. So how you do that? You just divide the system onto different cells, and what you need to do is just check the neighbor cells if the particles inside those cells are inside the cutoff. So you don't need to check the entire system; just need to check the neighbor cells. So if the size of the cell lists, the size of the cells, you can change, and it's also the same as the skin. It's also a trade-off. If you have a larger size of the cells, imagine that you use R-cut. If you use R-cut, one particle in the center, you'll have up to this spherical around the center. So you have a lot of empty, a lot of parts of the cells that will be checked, or with particles that will be checked, but that are particles, sorry, that are not in the inside the R-cut. So you'll have a lot of false testings that you don't need. If you decrease the size of this cell list, you'll have less failures on testing the particle, but you have to check first and second and third neighbors, which will take a longer time. So you just this is also a trade-off. What LAMMPS use by default is consider the size of the cells as half of R-cut, so half of R-cut, and this is just an optimization. Okay, so the first computation is the bottleneck. So one thing, this you can have these optimizations, but one important part of molecular dynamics is that it can be parallelized, and mainly this force computation needs to be parallelized. So what we can do is just to divide the system, we divide the space in equal sized regions, and just send them to different process or different cores or whatever you use. And so you have this region that is divided for different numbers of particles are divided in the region, and you can send them to different processors, but you still need to communicate some once in a while, because our particles that change from one side to the other. But one thing that is important is that each time that you want to compute the force, so you look for all the particles in your system, in your inside one process, you check to all the particles, and if you go to these particles in the limits of the process of the region, if you want to check all the list of particles, you'll have to go to the other process. So you don't want to communicate in the middle of checking all the parts of the force, mainly the force computation, which is it's a heavy part, it's a bottleneck. So what is done is that you have these red regions, and these red regions, every particle that belongs to one process and that is inside of this red region will be a ghost to the to the process, the neighboring process. So in the inside this neighboring process, you'll get these particles, and you get these ghost particles over here that are inside this, that belong to the null process, but will be also considered here, and they will be checked for the force computation. So that way you have the force computation completely separated between process, and you just need to update the communication in the time step just before the computation of the force. And you need to communicate that time, and not when you are computing the force. The size of this red region will be the R cut plus the skin, just to keep the particles. At least you have all the particles in the neighbor list, in the Verlet list. So how to divide the system? Usually LAMMPS do it automatically. You can also check it yourself. Can do it yourself. So how LAMMPS optimize is that, imagine that if you have a rectangular system, and you can cut it in this direction or in a longer direction, but in this direction the red region will be a lot smaller than in this direction. So the LAMMPS always choose to cut the system in a direction where the red region is smaller, and then you have less ghost atoms, and the communication will be a lot shorter. So this is an optimization. Of course, they already have implemented all the other techniques, just different size for the process that take into account the number of particles, or they can also dynamically change the size of the regions that the process have allocated, and it should depend on the system. But by default, this is the method that we have, just equally sized regions of our system. Okay, so this is the parallelization. So now we'll talk a little bit about the important physics part of this ActiveMatter course. So you already saw this in I think I could talk, and so you saw a bit about Brownian motion. I'll just talk about how LAMMPS implements Langevin dynamics. So Langevin dynamics is given by these equations of motions. You have the regular Newton equation plus some terms that take into account the direction with the fluid, the solvent. So you'll have the drag, the drag force, and the random force due to the kicks of the fluid. So the random will be just a random number with the average with a mean value of 0, and a variance of that is related to the temperature and to the basically the diffusion coefficient of our particles. And we also have, if you have a solid, or if it's not only at the point you have a solid object, you'll have also rotational motion around one axis. So you'll also you also need to solve the Langevin equation for rotational motion, which is similar, but instead of the velocity, you'll have the angular velocity, but you have torques, and it's the same principle. But in these are the important parameters. You'll have the damping parameter, and the relation with the damping parameter and the temperature will give us some the diffusion of the particles in the Brownian regime. So using the Stokes-Einstein relation, you'll get these diffusion coefficients, get the translational diffusion coefficient, which will be kBT over the damping parameter, for what we have here, and the same for the rotational diffusion coefficient. As you can see, the damping parameters are different. LAMMPS use the damping time, which is the mass over the damping parameter, or in the case of the rotational damping time is the inertial over the damping parameter. But LAMMPS does not take in account the rotational damping time, just use the translational damping time, and then just have a factor, scaling factor for the rotational damping time, which will depend also on the shape of the particle. For instance, if you have a spherical particle, this is taken by the Stokes-Einstein relation and the Stokes-Einstein-Debye relation for the rotational, and you'll get the ratio between the two. And so our LAMMPS solves the equations of motion is like this. LAMMPS implementation is like this. So instead of using the damping parameter, you have the damping time. So you have to put here mass over the damping time. And the same in the random term. As you can see here, the value is outside, but it comes from the variance of this the random number. And as you can see here, but then the random numbers of LAMMPS, as I say in the notes, if you check my notes, they use an uniform random number, which is faster and gives the same values for if you have a large number of particles, but they have to do a correction, and I also explain in my notes. But what we have here is that we have the relation, but we have the two, the translational motion, the translational motion and the rotational motion. And as you can see, use the damping time of the translational motion for both cases, and just have this factor, this scaling factor for the relation between the damping time for translational and the one for the rotational motion. Later, when we'll talk about the active particles, we'll use this scaling factor to control the damping, the rotational damping time, which will be important for Brownian active particles. Okay, so as the last thing I want to talk today is about reduced units. So this is a part where a lot of people get confused in the reduced units, and LAMMPS has the possibility to use international units or real units, which a lot of people use. But if you want to rescale your model to different scales, and if you found something that you want to rescale, so it's quite complicated, and you are also working with very small numbers, which could have numerical problems. And so I recommend to use the reduced units. As a reduced units, just use the Lennard-Jones potential as a reference, but this is a reference. So the size, this is, for instance, the Lennard-Jones potential has this sigma. So the sigma is the position where the potential crosses the zero line. So potential is repulsive, and then it goes to attractive, and this point where it is zero, this is the value of sigma, and just use that as a reference. So sigma is the reference value of distance. So if you just change if you change the potential to the Lagrange potential to 10, the sigma 10, it will be 10. The reduced unit will still be 1. Okay, it will be 1 sigma, but the values that you have is 10, and that's your reference. The same as you choose the size of your particles. You choose a radius of 5 or radius of 10. Use that as a reference. This is important not because you're using the Lagrange potential, but this will be a reference between all the values. So if you use the 10 sigma as a radius, you can relate that to the value at the real value. I show that on my notes. I try to explain with some examples in my notes. If you use the temperature to see the energy scales, and then you can get the time scales by using the mass of the particles, and you can get the distance by using the radius. So you have your mass of the particle, your radius, and use the temperature as a times energy scale. You get almost all of the variables. One thing that I like to use when using Langevin dynamics, or because since Langevin dynamics recovered Brownian dynamics above some damping time, you can use just the Brownian time. So the time that one particle needs to cover one diameter square, one of its diameter square, which can be a good reference then to use for real systems, and use that time as a time unit, for instance. But you can then choose what you prefer. So I think I will finish my first video here, because the next video I will go directly to the website of LAMMPS, and then just to the command line. So PowerPoint will stop here. Okay.